All right, welcome. Today we are diving deep into one of our most amazing senses, hearing. We're going to follow a single sound wave on its wild ride, all the way from the air around us, deep into the machinery of the human ear. And to really get our heads around this, we're going to channel a classic sci-fi flick. Just imagine we're shrinking down, hopping onto that sound wave like it's a tiny submarine. Our mission? To take a fantastic voyage and see for ourselves how hearing actually works. So that's the big question, right? How on earth does a simple vibration, just a wiggle in the air, travel through this incredibly complex biological machine to become something our brain actually understands as sound? Well, let's find out. Okay, every great journey needs a map, and this is ours. This diagram shows the three main territories we're going to travel through. First, the outer ear, then the middle ear, and our final destination, the inner ear. Let's start right at the beginning. First stop on our tour, the outer ear. This is the only part of the system that's actually in contact with the outside world. It all starts with the pinna. You know, that's the fancy name for the weirdly shaped flap of cartilage you hang your glasses on. Its main job is to act like a satellite dish, catching sound waves and funneling them inside. And here's a fun fact. When Van Gogh cut his off, he didn't actually make himself deaf. The pinna helps, for sure, but it's not absolutely essential for hearing. Okay, so from the pinna, our little sound wave gets funneled down this short, kind of crooked tube, the ear canal. It's only about 2.5 centimeters long, and it's basically a straight shot to our next major landmark, the eardrum. But here's the thing, the ear canal isn't just some boring pipe. Its precise shape and length make it resonate, kind of like a flute. It acts like a natural amplifier. And get this, it specifically boosts frequencies in the 1,000 to 6,000 hertz range. That is the exact sweet spot for human speech. It's like our ears are literally pre-tuned to listen to each other. How cool is that? Our sound wave has now rocketed down the ear canal and bam, it slams into the eardrum. This is the gateway to the next stage of our adventure, the middle ear. So, welcome to the middle ear. It's this tiny air-filled chamber. Now, this chamber is connected to the back of your throat by a little thing called the eustachian tube. And that tube is the reason your ears pop on an airplane. When you swallow or yawn, you're just opening that tube to equalize the air pressure on both sides of your eardrum. Now, inside this tiny room are the real stars of the show, the ossicles. And these are literally the smallest bones in your entire body. You've got the malleus, or hammer, the incus, or anvil, and the stapes, the stirrup. They form this tiny, delicate chain that stretches right across the middle ear. And their job is, well, it's absolutely crucial. Which brings us to the central engineering marvel of the whole system. The middle ear's function is so important it gets its own special name. It's an impedance matching machine. So what does that even mean? Well, the ear has to solve a huge physics problem. Think about it. It's easy to make vibrations in thin air, but it's really hard to get those vibrations into a dense fluid. It's like trying to shout at someone who's underwater. Most of your voice just bounces right off the surface. The ear faces that exact same challenge. And here's why. Air has what's called low impedance. It's easy to get its molecules moving, but the fluid inside our inner ear has high impedance. It's way harder to vibrate. If we didn't have a solution for this, almost all the sound energy would just reflect away, and the world would sound incredibly muffled. So how does the ear solve this massive physics problem? With a beautiful three-part mechanical system. First, it concentrates the force. The eardrum is way bigger than the tiny spot that the stapes bone pushes on. It's like focusing all your weight onto the tip of a thumbtack. You get a huge amount of pressure. Second, those three tiny bones, the ossicles, act as a lever system, turning big, weak vibrations into small, powerful ones. And third, the eardrum itself has this cool buckling motion that adds even more oomph to the system. And the result of all this brilliant engineering? The pressure from that original sound wave gets amplified by 20 to 30 times. That is a massive power-up, and it's exactly what's needed to get that fluid moving in the inner ear. And that's why biologists and engineers call the middle ear an impedance matching transformer. It's a fancy name for a biological device that perfectly solves this problem of transferring energy from thin air to thick fluid. It's just brilliant. So there we have it. Our little sound wave, now supercharged and massively amplified, has made it through the outer and middle ear. It has arrived right here at the oval window. which is basically the front door to the inner ear, where the real magic is about to begin. The mechanical energy has been delivered. The physics problem is solved. But what happens next? How does that physical pushing and vibrating get turned into the electrical signals our brain actually understands as music or speech or, well, sound? We'll find out what happens when we cross that threshold in our next explainer.